In this example, we have two wooden members joined at the cross-section with a simple scarf splice. And so we know that the maximum allowable shearing stress in the glued splice, the glued splice is 60 psi. So what we want to do is figure out what the largest load that can safely be supported and what the corresponding tensile stress is in the splice. Now, just so you know, typically when dealing with glues and epoxies, their strength is going to be in the normal direction. They're actually very weak in the shear direction comparatively. So if you ever are gluing joints together, or if you've got something that's glued together with super glue and you're trying to get it apart without breaking it, pulling on it's usually not the best way. You want to slide into it. It's actually when you're assembling things, this is where pins become helpful. And it's not really that the pin is increasing the strength of the joint a lot, but what it's doing two things. One, that hunk of metal in the shear plane does help with the strength, but also because the way the pin's jammed into the joint, now the glue has a bunch of normal forces acting when you go to push on it in the shear instead of just the shearing force. But anyway, let's get started and take a look at this. And so let's get to a clean piece of paper. And so what do we need to do? Well, we're trying to figure out the largest load. And so we're going to look at our shearing stress, which is going to be P over A naught sine theta cosine theta. And that's what the equation we're going to have to solve. So now a couple things to look at is we're going to need to know what A theta is. And we have that there. 3 inches times 5 inches. So we have a rectangle of 15 square inches. Now we also need the angle. Now we look at this and we're sitting here and go, okay, it gives it to me at 60 degrees. We have to be careful because once again, remember what we said before, it's got to be on the vertical. So if I look at this as my cross section, and if I take it and rotate it to match the way that we had drawn the picture when we set up the equations, this is what we have. That's the angle that we're given. Remember, all of our equations are based off of the angle from the horizontal. And actually, I should probably draw it here instead of there. And there goes part of the picture. So we're not looking for that 60-degree angle from there. We're looking at what the angle is from, and you know, that's a really bad, I'm just not drawing it very well. Let's try that again. So it's here. If I rotate it, that angle is 60 degrees. What I want to know is the angle from the horizontal. That's theta there. And so we've got a right triangle with the way that we drawn that. So actually, if we look at it, our angle is 90 degrees minus 60 degrees. So our angle should be 30 degrees. Okay, and from there we can go and solve the first part of the problem, where they tell us what our shear stress is. So if we go back here, 60 psi. That's the maximum shear load that we have. So if I know that, I can use that to find what the maximum load that I'm applying. So I have my maximum shear stress, and I want to figure out what load is going to cause that maximum shear stress. And so I'm just going to rearrange my equation a little bit, because I want to have P on this side and theta on that side. So I'm just going to multiply through. So tau theta divided by sine theta cosine theta is going to equal that value of P. And from there, I am just going to plug in my numbers. So 60 psi times 15 inches squared. That's going to give me pounds, which is great. It's fine. Sine 30, cosine of 30. So if I go and I plug all those numbers into my calculator, I will get 2,785 pounds. And we can use another, just like we have KSI for thousands of pounds per square inch, this would be 2.078 kips. And what is a kip? A kip is just 1,000 pounds. Okay, great. So we found what the maximum load that we can apply on this joint without it failing. And so the next question becomes, what is the corresponding maximum normal load? So we know that that's going to be P over A naught cosine squared theta. And we have all the information. We can just plug it in. 2.0785 kip divided by 15 inches squared cosine squared of 30 degrees. Where did it go? Sorry, I hit the wrong button, so we got blackout. No, they are not attacking my computer to make sure that you do not learn this. It's just my own error. So anyway, let's go, and if we throw that into the calculator, plug it all out, what we get is 0.1039 KSI, so thousands of pounds per square inch because I have the kip in there, or I can just rewrite this as 103.9 PSI. And so there is my corresponding normal stress with that at the load that gives me the maximum shearing stress. All right. If you have any questions, please let me know. Otherwise, I'll see you in the next video.